So, oh, now there's sound. Yeah, I'm going to talk about lattice gauge theories. So simulating gauge theories, I think, is one of the most promising applications of future quantum computers. And I'll try to give a bit of an overview of what I think are the key challenges that need to be addressed, and give you a little bit of a guide through some of the things we've been done specifically in Innsbruck, we've been doing to address these challenges. So let's start with why simulate gauge theories in the first place. And in my opinion, a good reason for that is that they're relevant to nature. So as captured by the standard model of particle physics, matter at a fundamental level interacts through gauge fields. So specifically in the piece of that describes the strong interactions, we know that quarks are interacting through the exchange of gluons, and the corresponding theory, QCD, could well be a fundamental theory of nature. And we know quite a bit about this theory already. We know this by experiment. For example, we know that we don't see quarks and gluons in everyday life, right? They're bound together because the theory is confining. So they form bound states, hadrons, protons, and neutrons that actually make up everyday matter. But if you go to high energies, the theory becomes asymptotically free. So you find that these quarks and gluons form a plasma, so you can sort of see the individual constituents. And this has been done for decades using extremely sophisticated collider experiments to test this. So we know quite a bit. And we also know how to compute certain things, and the standard way to do this is called lattice QCD. So it's a lattice regularization where you put these quantum field theories on a space-time lattice, and then you try to simulate it. And the gold standard for this are Monte Carlo simulations. So for this, applying this methodology, for example, we know very well what's going on at finite temperature in QCD, but we do know less well what's going on if you go to high densities of the fermionic matter. So for example, it's not really possible to describe what's happening maybe in the inner workings of a neutron star. And the reason for that is that there is a computational problem with these approaches. It's so-called sign problem. That's a generic thing that happens when you go to finite fermion densities. For example, you also have it in condensed matter in the Fermi-Hubbard model if you go to finite doping. It's basically the same problem. And the situation is even worse if you go to real-time evolution. For example, if you were to attempt to simulate what's going on in such a heavy ion collision from first principles, it's basically doomed to fail unless you do severe approximations. So this is the reason why I want to do quantum simulations of gauge theories, because this might be able to access these phenomena. So this is the high energy picture. Gauge theories, especially on the lattice, however, are much more versatile. And I just want to emphasize here that they also play a role in condensed matter physics, for instance. So there is not just these confined phases, but there's also so-called topologically ordered phases where the gauge fields are deconfined. And this topological order has also applications in quantum information science itself. For example, certain quantum error correcting codes are based on these properties, and which is another nice reason to study these models. So the idea of simulating lattice gauge theories using quantum devices is actually an old one, but it has become an experimental reality rather recently in the last decade or so, and I want to give you a little bit of an overview where we stand right now, and also emphasize that there's many different platforms and many different approaches. So historically, the first experiment that tackled a sort of very small scale lattice gauge theory with very few lattice sites was performed in Innsbruck. Well, I wasn't there at the time, but I guess I have to say this anyway. So this was a small digital simulation where you simulate a few Trotter steps in real time on a very small lattice, and it's quite impressive to see where trapped ions have come in the last decade. So one of the most sophisticated simulations that is also relevant to certain aspects of quantum error correction was this experiment where people realized a non-abelian topologically ordered phase on a trapped ion quantum computer. But there's not just digital approaches. There's also analog simulators, and especially analog simulators based on ultra-cold atoms in optical lattice have been extremely successful for studying Hubbard-type physics, for instance. So starting from simple sort of small-scale building block examples, people realized relatively large arrays of 100 atoms in an optical lattice, and if you play some tricks, you can make the system behave as a gauge theory. And as Monica, for example, yesterday was pointing out, is that these systems are in a sense, much more coherent and reliable to perform long real-time evolution. So, for example, the thermalization of gauge theories has been studied in this context. More recently, as we heard from Misha yesterday, Rydberg atoms have entered the game as another way to perform not only digital quantum computing, but also analog quantum simulations. And in fact, the strong Rydberg interactions, these strong encodes local constraints that you can sometimes interpret as a certain type of gauge theory. So the largest 2D analog simulations of lattice gauge theories have actually been performed in this setup. And then finally, there's also superconducting qubits, and I think here an important feature to the community was that these systems, especially from IBM, became available through the cloud, so theorists could actually play with these models. And overall, there's many more theoretical proposals, and this is a sort of personal collection. I encourage you to have a look at more recent reviews to get a full picture of the story. Okay, but let's actually delve in a little bit more into the details of what makes a gauge theory and how these systems are maybe limiting at the moment, and what we need to leverage to tackle the outstanding questions, and ultimately maybe QCD, as I was alluding to in the first slide. So what is a gauge theory? Gauge theories are sort of relatively complex models with degrees of freedom that you're maybe not super used to when you think about more spin models, let's say. So the generic setup is this: you have a lattice, a spatial lattice when we talk about the Hamiltonian formulation, and there's two types of degrees of freedom. There's gauge fields that live on the lengths of this lattice, and there's matter fields that live on the sides. And the defining feature of a gauge theory is the presence of local symmetries. So this is what we call gauge invariance. So there are operators, G, associated to every vertex that sort of connect the gauge fields on the links to the charges that is carried by the matter. And the constraint is that the Hamiltonian must commute with this. So this severely restricts the type of terms you can write down. For instance, there's always a sort of local gauge field term that's like an electric energy that tells you what kind of energy each configuration costs. But then the real interesting physics actually only emerges in 2 or 3 spatial dimensions, which is when these gauge fields interact with themselves. And the only way they can do this is by these, or the simplest way they can do this is by these plaquette operators. So these are the terms that actually drive the physics of topologically ordered phases in 2D, but they're also key to describe really the way how confinement plays out in the real world. So that's kind of a nasty thing, and that's something I will be focusing on in a little bit more detail. And then furthermore, this, well, I haven't really told you how these operators look like, but they are always related to some symmetry, and this symmetry also dictates the nature of the degrees of freedom that live on the links themselves. And if you talk about the standard model, for instance, QCD, the gauge group is SU3, and this dictates that the local Hilbert space of the gauge fields is actually an infinite dimensional Hilbert space. So these are bosonic fields, not just spins, not just two-level systems. So we need some way to truncate these fields if we want to represent them on any quantum device. And that's another problem that needs to be tackled. And then similarly, well, I was alluding to this challenging phase diagram, but actually the challenge there is with when you couple to fermionic matter. So how to treat fermionic matter and how to couple these into the story is another subject on its own that I'm going to touch on briefly. So generically, the operators look like this. You have fermions or matter degrees of freedom moving from one side to the next, and through this sort of hopping process interact with the gauge field in between. And then finally, if you insist on defining a quantum field theory, all of this is sort of a regularization that you need to remove at some point. So there is a question of taking a continuum limit of this, which is well established in the sort of Euclidean Monte Carlo community, but in the Hamiltonian picture that is more suitable for quantum simulations, I think there is still a lot to learn how to do this well, nicely and efficiently. So this is also the overview for the rest of the talk. So I'm going to touch upon these things very briefly. And I would like to emphasize that maybe now is the time to reevaluate the way we actually phrase these models and address it a little bit more sort of from a quantum computing perspective. So this maybe requires a little bit of a different thinking. And then I already mentioned that these plaquette operators are kind of nasty, so they don't come very natural in an analog setup. So we need a little bit more programmability and flexibility, and ultimately I think digital approaches are the way to go to realize these complex interactions. And concerning these the actual degrees of freedom, I would like to advocate that it's nice to sort of keep the locality of these models, to keep the locality of interactions, and this doesn't work if you replace these individual degrees of freedom maybe by a bunch of qubits. So maybe you want to use multi-level systems to encode them directly, so we work with qudits instead. And then similarly, one might ask, for example, thinking about neutral fermionic atoms, we actually have fermions in nature, so maybe we can leverage this, as is already done for simulations of Fermi-Hubbard models. Can we maybe leverage this to represent the matter degrees of freedom in a complex gauge theory as well? And then finally, I'm not sure if I'm going to have time about this, briefly going to touch about some physical questions. Okay, so let's start with the Plaquette interactions, and let's delve a little bit deeper into the details. So let me tell you how these operators actually look like. So for this, we consider only the gauge part of the story, so it's a pure gauge theory. There's only gauge fields living on the links, and as I said, the local Hilbert space is spanned by a basis, or is given by a group. So the symmetry group, for example, could be an abelian group, U1, could be Zn or something like that, or in the simplest non-abelian case would be SU2 or maybe a finite subgroup of that. And then you span the finite dimensional, you span a Hilbert space by labeling basis elements with elements of the group. And then the Plaquette operator is constrained by the symmetries of the model and always takes a very generic form. So it acts on 4 degrees of freedom labeled 1, 2, 3, 4 around this Plaquette. And in this basis, I label these elements G1 to G4. And the operator always looks like that. It's the trace of a representation matrix of this particular product. So if you don't know what that really means, think about a function that assigns a value to specific gauge field configurations. And it's not the most crazy operator you could write down. In fact, in this basis, it's a diagonal operator, right? It doesn't introduce any transitions. And it's a function of a single variable. It could be a function of 4 variables. And it's this particular group product that is sort of enforced by the symmetries of the model. And this suggests a relatively simple decomposition of this 4-body operator, which involves this, what we call controlled group multiplication gate. So there's a special sort of 2-body operator that acts on 2 links, and it changes the value of the first gauge field link by asking the second link, what's your value, and multiplying. Okay, so this is sort of like a controlled X, if you think about it, but the general version of that for arbitrary groups. And this suggests the decomposition of this operator, where in the circuit language you think of these 4 lines representing the gauge field states. Then you sort of write the information of the second link into the first, the third one, the fourth one. So you turn the first link into this particular configuration, such that the gauge field, the Plaquette operator, then acts as a local operator. And this suggests a sort of co-design strategy where you say, let me represent the gauge fields themselves by qudits of the size of the group. And then the only thing I need are single qudit operators and this very specific or like special controlled group multiplication gate. And this strategy is completely general. It applies to every group, and you can do it once you have a finite group. And for example, you can then think about constructing trotterized real-time evolution algorithms with sort of this gadget as a key ingredient. And this brings us to the next point: is well, how do you actually build a qudit quantum computer, and how do you implement these particular operations that I was highlighting? And here, once again, I'm appealing to atomic hardware simply because we sort of get multi-level systems as qudits for free in nature, with a little bit of caveats. If you think about, for instance, hyperfine structure of atoms or trapped ions. In fact, in Innsbruck, we have Martin Ringbauer, who's an expert on trapped ion quantum computers. He's recently demonstrated that the same technology that is used to build qubit trapped ion computers can be extended to the multi-level case. So you can actually build qudit quantum computers using the same technology, and you can leverage all these bunch of levels that are available, for example, in calcium plus ions. And this is already being explored in the context of gauge theories. Just to give you another alternative, you could also ask where else do we have many levels? And neutral atoms, specifically alkaline earth atoms, are another answer. And here we suggested one architecture recently with one of my favorite atoms, with the strontium 87. It has a large number of levels available. If you don't know the details, just there's many of them. And our experimental colleagues have perfected the control of internal degrees of freedom, more or less. So we heard about this a little bit yesterday also. So I'm not going to comment on how to do single qudit operation, because they're sort of, they're more or less settled. The question is, how do you entangle multiple of these atoms now? And here I'm using this sort of popular idea of coupling to Rydberg states. And I'm briefly going to walk you through a particular type of entangling gate, which is a controlled unitary operation that you can use to build these controlled group multiplication gates I was mentioning. So this operation is acting on 2 qudits. it's changing the state of the first qudit if the second qudit is in a particular control state. Okay. So the idea of the implementation is actually a relatively straightforward extension of these blockade ideas. So I have a target qudit and a control qudit. I don't care exactly how you control them individually, but I want you to be able to couple to a Rydberg state, and I want you to be able to bring them so close together that they blockade each other, so they cannot be simultaneously excited to the Rydberg state. And then you can run a protocol like this. First act with a unitary on the target, somehow through an excited state, for example. So this realizes this operation, but unconditionally on what the second qudit is doing. Then excite the control, so to say. Turn the control on by exciting from a specific state J to a Rydberg state. And then in the third step, you act with the same, or with the inverse unitary from the first step, this time making sure that your population has to pass through the Rydberg state. So this makes sure that if the control was on, this operation doesn't happen, right? Because it's blockaded. So it wasn't on, then this gives you just the first line. However, if it was not in that particular state, it just cancels the operation of the first step, and this gives you the second line. And then afterwards, you have to clean up the control, so to say. So this is a sort of generic way you can build these controlled unitary gates. And if you have already single qudit control and you add this gate to your gate set, this is actually universal. So you can use this sort of architecture to build a universal qudit quantum computer if you wanted to. And moreover, for what I'm interested in, this is also, I haven't shown this to you, but there's also sort of efficient decomposition of the controlled group multiplication gates I was relying on using these specific controlled unitaries. Okay, so then we were asking ourselves, okay, gauge fields check, sort of, as qudits, large qudits. Can we play the same game with fermionic matter? So let me remind you how the interaction here looks like. So for general gauge theory, it looks like this. Fermions are hopping from one side to the next, and they interact with gauge fields in the middle. And in contrast to many sort of condensed matter models where you have maybe spinless fermions or two-component fermions, for a general gauge group like SUN, you would have n-component fermions here. So it's already good to think about these atoms like strontium, which have many internal states. And then they also sort of change their internal states potentially while interacting with the gauge field. So this looks a little bit complicated. But I ask you to believe me that the same calculation that works for the plaquette actually also works here. So if the fermions are sitting on a single spot and not moving around, like the strontium atoms, you don't really see that they're fermions, right? They're just multi-level atoms. So they behave like qudits. You only see the fermionic statistics if you delocalize them, if you actually have spatial superpositions of these fermionic atoms. So if they're fixed in place, we can treat them as a qudit, and we can play the same kind of controlled group multiplication gate to entangle the gauge fields with the fermions, so to say. Again, if you do the math, you see that this, for example, for a Trotter step of this Hamiltonian, it basically turns this unitary operator in the middle to a delta AB. So the only thing that remains is a direct tunneling process. So this way you disentangle the sort of gauge field matter field interaction to just a fermionic tunneling. Okay, so we have single qudits operations. We have these controlled gates that work also with fermions. The thing that's missing is a digital tunneling operation. So we were asking ourselves how we do that. And this is actually also relevant maybe in a more general context for like fermionic quantum information processing. So the idea is, again, use our like favorite types of atoms, which have another few nice properties. For instance, you can trap. You can individually, there's certain specific configurations where you can individually shine optical trapping potentials for this ground state manifold and this excited state manifold independently. So you can play a game where, for example, you fix certain atoms in positions, let's say the links, which play the role of your gauge fields, and then other atoms you use as your fermionic degrees of freedom, and maybe you move them around even with, like, the fixed ones, maybe an optical lattice, the ones for moving around, you maybe use this tweezer technology that we've heard about. So then you can implement what we call a shuttle gate. So the idea is this: you have your specific locations where you want to tunnel, so maybe a storage optical lattice, and then you bring a sort of transport tweezer on top of one of these locations. And then you do an internal pulse to completely transfer your atom from this ground state manifold to the excited state manifold. Then you move the excited state sort of by hand over to another position, where you then perform an internal pulse that creates a superposition. Okay, so you've created this superposition, and these are fermionic atoms. Maybe I should have said that, strontium 87 is a fermion. So there's, for example, Pauli blocking naturally occurring. And then you delocalize the superposition by hand. Okay, so you have this local superposition, but then you move the excited state by hand to another location, and then you undo the first pulse. And you can convince yourself that this is actually identical to a physical tunneling process. Okay, so this is a little bit of a theorist's dream, to be honest, because experimentally this is quite challenging, because you need exquisite control over the motional degrees of freedom to actually leverage these fermionic statistics for free. As sort of the ingredients have been demonstrated individually, but putting it all together is probably still quite challenging. But I think it's a nice idea to sort of leverage all the nice properties we have in atomic systems and guide the design of our algorithms to do this sort of simulations. Okay, how am I doing in time? Okay, so I've talked a lot about designing hardware or architectures that are tailored to gauge theories. Let me now spend the last few minutes on sort of this question of how to actually phrase the problem. And I've been lying a little bit to you, because I was basing everything on the fact that I have a finite gauge group which underlies these controlled group multiplication gates. Unfortunately, if you're interested in models like SU2 or SU3 lattice gauge theories, you cannot use finite groups, because there is no sequence of finite groups that actually converges to these models. So this truncation that you need to do, because you only can control a finite number of degrees of freedom, is ultimately uncontrolled. So you have to do something else, and what to do exactly is still under debate. So here is our proposal, which is related to a so-called Irab truncation. So if you're not so familiar with the math, let me give you an intuitive picture. So you can think of these basis states that are introduced before as position states. So you have your group, and this basis G that I was writing down is sort of the position basis in that group. But there is always a sort of generalized Fourier transform that brings you to a momentum space. And for SU2, the momentum space sort of looks like this. So there's labels JMN. So there's a quantum number J that labels all the Irabs of SU2, 0, 1/2, 1, up to infinite spin. And then there's a pair of magnetic quantum numbers, so to say, coming with this. So this is an infinite dimensional Hilbert space and sort of an equivalent description of the space. So what you do often in other algorithms as well is just truncate the Fourier basis, right? So here the same strategy would be you truncate this model at a highest spin representation. And now it gets a little bit technical, so let me skip the details. But the idea is, if you do this by hand, sort of, then you lose certain symmetry-related properties of these models. For instance, there is no analogous thing like this controlled group multiplication gate that we can use to write down nice circuits. So we were looking for something else, and it turned out there is a way around, which is by using so-called deformations of these groups. So there is an additional parameter, which is a root of unity. So there's an integer k related to that turns out to actually implement this truncation in a way that also changes the matrix elements of the Hamiltonian in a little bit. So without going too much into the details, the result is that you can rewrite this model of pure gauge theories for SU2 that lived on a square lattice as a setup where you have qudits living on links of a sort of honeycomb lattice, because you split these vertices. And then you get sort of nasty plaquette operators that I don't want to write down, but so they act on actually a bunch of degrees of freedom. So there's, at first sight, it seems to get even more complicated. But the advantage what we gain is that we actually can leverage algebraic properties to write down exact circuits independent of the truncation we do. And ultimately, the key element here is what we call an F move, is a certain type of change of this basis that we have chosen to decompose these plaquette operators. So similar as in the controlled group multiplication gate, there's another set of gates that allows us to do this diagonalization analytically for arbitrary truncations. And once again, it's realizable with single qudit gates and these controlled unitary gates that I was introducing earlier. Okay, so I'm happy to discuss this in more detail, but I think this goes a little bit beyond the scope of this talk. If I have a few more minutes, I do? 3, 2, 2.5, okay. I can briefly touch maybe on the physics of these truncations, because I think that's quite interesting on its own right. So you can ask yourself, if you do these regularized models, these truncated models, what's the physics that I get? And it turns out that here we get physics that is interesting from both condensed matter and high energy perspective. So you can write down very simple tensor network sort of ansatz. It's actually more of a mean field construction, which contains the limiting ground states of the model. So there was this, if you remember, there was this Hamiltonian that had, in the pure gauge case, there's an electric term, it has this magnetic plaquette operators, and there's a coupling strength that favors the electric terms or the plaquette terms on one side. And with this ansatz, we can get a feeling for what are the type of phases we can expect. So in the strong coupling limit, we get a phase that is confined, which you can see here with the plaquette expectation value. It's basically not fluctuating. But then for weak coupling, you transition into another phase, which turns out to be topologically ordered. And as you increase this cutoff, you see that this sort of spurious topologically ordered phase vanishes. This is what we want from a high energy perspective. From a condensed matter perspective, you're maybe interested in what's actually going on in this phase. And it looks like there is a phase transition in between. And the nature of this phase transition is actually an open problem and would be interesting to study on its own right. What's interesting, or what I found sort of surprising, is that for this simple model where we can compare to existing lattice simulations, we find that we increase this cutoff, we seem to converge to what is well known. So it seems like these models are well behaved and would be interesting to study the nature of this transition in a little bit more detail. Okay, so with this, I'm coming to the end. I hope I've given you a bit of an overview on this idea of co-designing both the hardware and the software. And I think this will be really crucial for the near future to ask our questions really sort of precisely. What is the type of problem we want to solve? What is the software? What are the algorithms that we need to implement these questions? And then also, can we maybe design the hardware in a tailored fashion? And while everything I've been saying was sort of in the NISQ era, in the sense of there was no error correction or anything in there, I think this advantage might actually carry over. And it would be an interesting question to study a little bit more in detail how you would write down, for example, specialized error correcting codes for gauge theories that take these hardware advantages into account and maybe even develop fault-tolerant algorithms. So with this, I'm coming to the end. Let me acknowledge all the people involved in these things. Here's the list of papers if you want to have a closer look. Let me also emphasize Peter was of course important in all of this, and Daniel, who's another postdoc from Innsbruck. And thank you for your attention.
Thank you very much for this overview. Questions, please.
Thanks for the nice talk. My question is, so this hexagonal lattice with the SU2K degrees of freedoms looks very similar to 11-Wen model. Is there any connection? And
there's a very close connection. So maybe it's not like here is the reference to the 11-Wen. So for this particular model, it's almost identical. The difference is for the 11-Wen plaquette model, you have this projector that implements the projection topologically ordered phase. So there is, in general, a sum of different plaquette operators with fine-tuned coefficients. Yes. Sort of the Kogut-Susskind model, or the deformed version that I'm writing down, has only the first one. Okay?
I see.
In the limiting case, it actually doesn't make a difference. The ground state of the projector is the same as the ground state of only the first one. It kind of makes sense if you think about it for a second. What is also different is that there's these triangle constraints in the 11-Wen models. I implement them sort of by hand. So this prefactor is infinite in that sense. Plus, I also add, haven't written it here, I always add a confining term. So there's a specific term that implements this electric energy that introduces the confined phase ultimately. So they're very closely related, and actually most or many of the things that we actually did are sort of inspired by this. Also the fact that these things appear and so on and so forth. So there's a very close connection to this.
Thank you.
Another question?
Yeah, thank you for the great talk. So back to the point of the NISQ devices, I want to ask you what size this system should have to get in a realm where it's hard for classical computers to make predictions. So how built should this system be constructed, and what kind of fidelity or quality of this operation? So you spoke about this also shuttle and transport. So if you have 1%, let's say, error, you excite slightly the motion, is that sufficient, or this would at the end ruin everything?
To be honest, I think I cannot give you a good quantitative answer, but I can speculate a little bit. So in my opinion, we're not going to beat lattice QCD anytime soon in realms where these Monte Carlo methods are applicable. So I would bet on scenarios where we're sure that there is no other competing method. And this is, I think, most likely going to be real-time evolution. And then it's again not super clear what we're going to find. Like again, to go to a sort of continuum field theory limit may be hard, but I would expect surprises once we have systems on the order of, let's say, qudits of size 10, system sizes 10 by 10, and real-time evolution which generates such a deep circuit that like tensor network methods are not applicable. I think then we're probably going to find something which is qualitatively new and that is not accessible in other means. But if you ask me for really quantitative estimates, I don't have them at the moment. Sorry.
Okay, more questions? Yeah,
Thank you. So I want to follow up on the pretty much last comment you made, namely that this is all for NISQ, and then maybe we can throw quantum codes on that and then make it maybe fault tolerant. The very first example you showed was very reminiscent of the Tori code. I think it pretty much was a Tori code. And so, well, you have a quantum error correction code right there. So my question is, how would you probe that kind of system, and how would you maybe look at phenomenology that is not protected by the error correction that the Tori code gives you, or is this an instance where you already have the error correction that you ultimately want? Yeah, please.
Yeah, so this is, I mean, it's a bit of a funny story, right? Because we have these topologically ordered phases which have certain sort of error correcting features. But what I meant is actually that we use another layer of encoding on top to study the dynamics of these. Okay? Mm-hmm. So it's not that because this looks like a Tori code, you're actually protected. No, because if we digitally realize the Hamiltonian evolution, for instance, we might just make errors in that model, and then the fact that this is supposed to become a topologically ordered phase is not necessarily helping us. Is that clear? So I think it will be necessary to put a second layer of sort of a proper layer of error correction on top to actually study these features, the physics of these features.
Thank you. That's good for now. Thank you very much.
Yes. Okay, but thank you very much, and it brings us to the next talk anyway. Let's thank the speaker again.